Okay, so yeah, so as I mentioned, because observers agree on what the speed of light is in their reference frame, right? So the speed of light is 3.0 times 10 to the 8 meters per second, no matter what reference frame you're in, as long as it's an inertial reference frame. They have some interesting consequences in, Okay, so let's build up that clock example that we were working on yesterday. Okay, so let's consider the following scenario. We have two people. We call them observers. Okay, one observer is stationary, and they construct a clock that's made up of two mirrors, and there's a beam of light that bounces between the two mirrors. Okay. And the way that this clock works is that they essentially imagine the beam starting on the bottom mirror. They measure the time it takes for the beam to travel up to the top mirror and then back down to where it started. Okay? And so by knowing that, well, it's a beam of light, so you know what speed it's traveling at, you know how far apart the mirrors are, you can use that to actually figure out the time it takes for the light beam to travel between those two mirrors. So that's why this thing is a clock, right? And so if we look at this formula right here, we can actually determine the time it takes for the light beams to travel between the two mirrors, right? The formula that I'm using here is just V is equal to delta D over delta T, right? So the speed that the light beam is traveling at, well, the speed is just C, right? The speed of light. The distance that it's traveling is, well, it starts at the bottom mirror, goes to the top mirror, and then back to the bottom mirror. So it's traveling a distance of 2d based on this figure right here, right there. And then the time that it takes to travel, we call this time, we give it a special name. Okay, so this time we call delta t sub s. So the sub s stands for stationary, and we call that the proper time. Okay. And the proper time is the time that's measured by the stationary observer. Okay. Okay, so I think we kind of got this far yesterday, and then we kind of drew the picture of what it would look like for the moving observer, but we didn't really do much for it. Okay. But now we can kind of dig in a little bit more. All right. Or that's the goal for today, anyways. See how far we get with it. Okay. So essentially, what I'm going to use here is I'm going to use the Pythagorean theorem to kind of figure out how far the light beam will have to travel in the moving observer's reference frame. Okay, so the triangle that I'm considering here is this triangle right here. Okay, so I just got to fix my headphones here. My wire always gets super tangled up. There we go, much better. Okay, so the triangle that I'm considering is this triangle right here. Okay, so let's consider this triangle, right? So this is a right angle triangle. It's a pretty simple right angle triangle, okay? And so what we can do is we can actually write an expression for this diagonal distance. I called it d prime there, okay? So this d prime, I can use Pythagorean Theorem. So d prime squared is equal to delta x squared plus d squared, okay? And so that's kind of my starting point for this, okay? Now I can keep going. I mean, the only quantity here that's sort of fixed in place is this d squared, okay? But I can kind of define a bunch of, or I can replace both d prime and delta x with certain things here, okay? So I continue this down here, right? So I have the same formula right here. D prime squared is equal to delta x squared plus d squared. Okay, so I've used the Pythagorean theorem. Now, since the observer, the moving observer is moving at a speed v, what we can do is we can write delta x in terms of v and the time that's being measured in the moving observer's reference frame. Okay, so let me show you what I mean by that. Okay, so our goal, we want to write delta x in terms of v and the time that's being measured in the moving observer's reference frame. Okay, and the way that we do that is we note that v is equal to delta x over delta t m. Okay, because again, velocity is equal to distance over time. But I have to be a little bit careful, right? It turns out that the way that I'm going to measure, or the way that I'm measuring time, is the time it takes for the object or the beam of light to travel from the bottom mirror to the top mirror and then back again, okay? And so it will actually travel a distance of 2 delta dx over delta t, okay? And so what I can do is I can rearrange this formula now for delta x, okay? So when I do that, I will get v times delta tm over 2 is equal to delta x. Okay, and what I'm going to do is I'm going to stick that into that formula. Okay. Now, similarly, I can express my my d prime variable in terms of the speed of light, right? Because essentially d prime, the light beam is going to travel along d prime. It's going to travel d prime to get from the bottom mirror to the top mirror, and then it's going to travel d prime again to get from the top mirror to the bottom mirror. Okay, so this light beam is traveling a total distance of 2d prime. Okay, which means again we can rewrite d prime in terms of the speed of light as well as the time that's being measured in the moving frame. So the way that we do that, again, very similar to what we just did, we note that c is equal to 2d prime over delta t sub m. Okay, and we can again rearrange this for d prime. So we note that d prime is equal to c times delta tm over 2. Okay. Is everyone with me here so far? Everyone see what I'm doing? Any questions? Okay, so I'm going to come down here in my notes. So I've kind of done all of this explanation already. So again, if anything seems weird, just double check there. But essentially, when I make those two substitutions, so when I plug in C delta T M over 2 and V delta T M over 2 for, so up top I saw that this thing was equal to, let me use a different color. I saw that this thing in here was equal to D prime. And I saw that this thing over here was equal to delta X. So I've made those two substitutions here. Now what I'm going to do is I'm going to expand both of these brackets out, and I'm going to just simplify, okay? Essentially, I want to isolate this expression for delta Tm, all right? So let's give it a go. So I'm going to expand out the left side bracket here, so I'm just going to move the square inside. So I'll get c squared times delta Tm squared over 4. And that's going to be equal to v squared delta Tm squared over 4 plus d squared. D squared is just hanging out. And then I want to move everything that is has a delta Tm over to the other side. Okay, so I'm going to take this term and I'm going to move it over. So I get c squared times delta Tm over 4, delta Tm squared rather, minus v squared delta Tm squared over 4. And that's going to be equal to d squared. Okay. Now I keep going. I can factor, right? I have a delta Tm squared in both of these terms, so I can factor that out. So delta Tm squared times, when I factor that out, I'll be left with c squared over 4 minus v squared over 4. So I'm getting closer, getting there. That's equal to d squared. And then I just divide, right? I divide both sides by this big bracket here. So I get delta Tm squared is equal to d squared over c squared over 4 minus v squared over 4. Not bad, not bad. Okay. But I actually know what d squared is, or rather I know what d is, right? I actually developed another formula right at the beginning that uses the stationary observer's clock, right? Remember that? So I had, all the way back at the start here, I defined the time it takes for the clock to tick for the stationary observer, so that's 2d over c, right? And so what I can actually do is I'm going to take this formula here, and I'm going to rewrite d in terms of the other variables. So when I do that, I get d is equal to c delta ts over 2, okay? And so what I'm going to do is I'm going to take this and I'm going to bring it down and I'm going to substitute it in for d in this expression here, okay? So I'm going to plug this in for d. And that way everything is in terms of speeds and time. So essentially I've removed any reference to distance, okay? Once I make this substitution in, it's as though I never had to consider distance in the first place, right? I put everything in terms of the speed of light or the speed at which the moving observer is moving and time, okay? And when I do that, I'm going to get a expression that looks as the following. So I will get c squared times delta t s squared over 4 over c squared over 4 minus v squared over 4. Okay. And if I pay close attention here, I notice that I have a divide by 4 in every single term here. So that just cancels itself out. Okay. So I'll clean that up slightly here. Delta Tm squared equals c squared delta t squared over c squared minus v squared. Okay. Now we're nearly done. This formula usually isn't written like this. We often multiply by 1 over c squared in both the numerator and the denominator. Okay, so it doesn't change anything, but it just makes it look a lot nicer, as we'll see in a second. So in the numerator, that will cancel out. When I move this into the denominator, what I'm going to find is sorry, this is delta ts squared. I'm going to have delta ts squared over, and then I have 1 minus v squared over c squared. that's equal to delta Tm squared. Okay. Whew, that was a lot. That was a lot of rearranging. But then I'm done, right? If I take the square root of both sides here, I get the formula for Tm, right? Which is kind of what I was looking for in this entire exercise here, right? The whole point of this is I wanted to figure out an expression for the time in the moving observer's reference frame as a function of the time in the stationary observer's reference frame, okay? So what this formula represents, it's a way of transforming between a moving frame and a stationary frame, okay? So I get delta Tm is equal to, if I just take the square root of both sides, I get delta Ts over the square root of 1 minus v squared over c squared. And that is the important takeaway formula there, okay? So I'll take a quick pause, and if you guys have any questions, let me know. Okay, so let's do a quick example just to illustrate that this formula doesn't really influence time that much in our everyday life. Okay, so let's say I don't know. Let's do a little case study here. Let's say that Jana is moving on a bus, and that bus, let's give it a pretty big speed. Let's say 50 meters per second. That's a pretty fast bus, right? Now Costa, you measure, you're stationary, right? And let's say that you do some sort of physics experiment, okay? So in this physics experiment, let's say you throw a ball up and it comes back down, and you start your stopwatch and then you stop your stopwatch, and the whole event of you throwing the ball up and the ball coming back down takes about 5 seconds, let's say, okay? So you do some sort of experiment, and that experiment takes about 5 seconds, all right? So what we want to figure out is, in Jana's point of view, let's determine how long that experiment would have taken. Okay, so Jana is doing the same experiment. Costa, you're standing and you're watching Jana's experiment, and you want to know, okay, do our experiments agree with each other? Is Jana also going to measure 5 seconds? Okay, so let's see what Jana will measure. So Jana performs the same experiment, and she measures her experiment taking delta Tm time. Okay. And what she'll notice when we plug in all these values here, we'll get 5 seconds over the square root of, so we get 1 minus v squared is 50 squared over c squared. Now c squared is a giant number, right? 3.00 times 10 to the 8. It's a giant number, and we're going to square it. So it's even more giant, okay? And so when we plug this into our calculator, let's see what we get. 5 over the square root 1 minus 50 squared over constant 28 squared. Actually, my calculator, when I plug that in, I get 5 again, because it literally was such a small difference that it just rounded. Okay, so let me try Wolfram Alpha. Let's see if Wolfram Alpha will get me a more meaningful answer here. So Wolfram Alpha. So I'm going to type this in, and we'll see what we get. 1 over the square root of 1 minus 50 squared over, I wonder if this will work, speed of light squared. Wolfram Alpha is usually pretty smart about that. We'll see if it actually works. Oh, incompatible units. Didn't work. Okay, I actually have to type this in. So close. 3.0 times 10 to the power of 8 squared. So look at how long it takes in Jana's reference frame. She gets a value of 5 point... How many zeros is that? 5.00000000000000069444444. So it's essentially 5 seconds, right? Really, there's no difference in the time that Jana measures in her experiment and the time that Costa measured in his experiment. Okay? So essentially, yeah, this is basically 5, right? There's how many zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros. That's so 5.2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then 6,944 seconds. Okay. And so essentially, the main takeaway from this example is that for everyday speeds in our everyday life, so 50 meters per second, the effects of relativity are negligible. They basically don't matter, right? And that kind of makes sense, right? Like, Jana, if you're measuring something on a bus, and Costa, you're measuring something on the sidewalk, you're going to agree with each other, right? Our everyday life would be very chaotic if you suddenly didn't agree with each other on time when one of you is on a bus, right? Okay. Okay, let's try a little bit more of an extreme example. Okay, so an astronaut is getting ready to go into space. Okay, so on Earth they're doing a bunch of tests, and they find that the astronaut has a let's say a heart rate, a walking heart rate of 75 beats per minute. Okay, so let's quickly figure out how long it takes for each heartbeat to happen. Right, so let's convert this to a let's convert this from beats per minute into the time it takes for one beat to occur. Okay, so if it's 75 beats per minute, if we multiply that by let's say 1 minute per 60 seconds, we would note that we would get a beat every 75 over 60. We would get 1.25 beats per second. Okay. And that's kind of a frequency, right? So to convert that into how long it takes for the each heartbeat to occur, we have to do 1 over that, right? So the time that it takes for a heartbeat to occur in a stationary reference frame, so this is our delta TS, is 1 over 1.25 beats per second. And when we do that, we get 0.8 seconds per beat. Okay, so each heartbeat will take a duration of 0.8 seconds to happen. Okay, and so basically you can imagine the astronaut as using a stopwatch, and every single time his heart beats, he resets the stopwatch, right? So every 0.8 seconds is how long he's resetting the stopwatch. Okay, and because the astronaut is on Earth, we're treating that as our stationary reference frame. Okay, so Earth is going to be our stationary frame of reference. All right. Okay, so now we throw the astronaut into a spaceship, and this spaceship is capable of reaching very, very high speeds. So let's determine the astronaut's pulse with respect to an observer on Earth, right? So Aiden, you're standing on Earth. Tycho, you go off in the spaceship, right? Aiden, what you want to figure out is how fast Tycho's heartbeat is in the space shuttle, or in the spaceship, okay? And so determine the astronaut's pulse with respect to Aiden's clock, so the clock on Earth, when the spacecraft reaches a speed of 0.10 c. Okay, so here we're told that v is equal to 0.10 c. So let's figure out the time it takes in the moving reference frame. Okay, so delta Tm is equal to delta Ts over the square root of 1 minus v squared over c squared. So that is going to be equal to, so we saw that each heartbeat took 0.8 seconds to occur over 1 minus v squared, so that's 0.10 c squared over c squared. Okay. And now what you're noticing in this question, actually what becomes pretty common in other like homework problems and whatnot, usually the speed that's given to us is some fraction or some decimal of c. Okay, and so what we can actually do is we can kind of expand this out, and we can just cancel out the c's. It'll just make our calculations a little bit cleaner, right? So let me show you what I mean by that. So you have 0.8 over, and then 1 minus, 0.1 squared, that's 0.01, right? Yeah. So 0.01 c squared over c squared. And here we can see that the c squareds will cancel out. Okay? And then that whole thing is square rooted. So we get 0.8 over the square root of 1 minus 0.01. Okay, so let's see what we get when we plug that in. We get a value of, so this is our delta Tm. Should have had that all the way down. Here, let's copy. Boom. Boom. So we find delta Tm is equal to 0.8040302522. Okay. And that is seconds per beat. Okay. And if we do these same calculations that we did over here, just in reverse, so meaning we do 1 over this answer, and then multiply it by 60. Essentially, we find that his heartbeat, if we convert this back to heartbeat, is 74.6240577.8 beats per minute. Okay. So note that the astronaut's heartbeat was 75 beats per minute on Earth. Now it's 74.624. So it's slower, but very negligibly slower, right? And notice what speed we're traveling at. We're traveling at 1/10 the speed of light, right? So you would imagine, oh, 1/10 the speed of light, that's pretty fast. You would figure that would have a bigger impact on the time. But even 1/10 the speed of light barely influences time, right? So that goes to show when we set the bus speed to be 50 meters per second, it shows that it's even way, way, way out of the realm of 1/10 the speed of light, right? So this shows that the effects really only become very noticeable at when the speed of the moving observer is very, very close to the speed of light, okay? So let's do one more example here. So it's the same question, but now the astronaut is traveling at 0.90 times the speed of light, so 90% the speed of light. So let's do this exact same calculation, but with the speed being 0.90 c instead. So this was B. For C, we're doing V is equal to 0.90 c. Okay. So same exact calculation, delta Tm is equal to 0.8 over 1 minus, or the square root of 1 minus 0.90 over C over C squared. Okay. So I'm not going to show as many steps here. I'm just going to kind of plug this in and see where it gets me. So 0.8 over the square root of 1 minus 0.9 squared. I get a value of 1.835325871 seconds. Okay, now that's pretty noticeable, right? On Earth, each beat took 0.8 seconds per beat. Now it's taking 1.83 seconds per beat. So that's actually a pretty significant difference, right? And again, if we convert this back into beats per minute, so again, we do the same calculation but backwards, we get a value of 32.69174208 beats per minute. So when the astronaut is moving that quickly, for an observer back on Earth, they're watching the astronaut measuring his heartbeat. What they observe is that his heart rate is actually over half as much, or just slightly over half as much as what it was back on Earth. So his heart rate is beating, or his heart is beating half as fast to an observer back on Earth that's watching the astronaut, which is pretty remarkable. All right. Okay, so now let's talk about length contraction. So what we saw in the above little explanation here is that time is affected, right? So if you have a reference frame that's moving relative to another reference frame, and a stationary observer looks at the moving reference frame, what they notice is that the time essentially gets stretched out, right? Or no, sorry, yeah. Time essentially, for the stationary observer, they look at the moving observer and they observe time ticking more slowly, right? So it's as though you took time and you just stretched it out, right? That's what dilation means, right? Time dilation, for a stationary observer, is one thing, and then you stretch it out and it becomes longer, right? So we saw, like, for the astronaut, each beat took a longer amount of time because the astronaut was moving close to the speed of light, okay? Now, you can imagine that, well, because time is affected, you could imagine that length is also affected, right? So let's start with the formula that we developed for time dilation, right? Now, what we're going to do to this formula is we're going to multiply both sides by v, okay? So v, again, is the speed at which the, well, we just said the astronaut, but the speed at which the moving observer is moving, okay? Now, suppose that suppose that they wanted to do some sort of measurement in length, right? So let's say that the stationary observer is standing off to the side, and what they want to figure out is, okay, let's say that the moving observer starts at a point A and they move towards a point B. So let's say we have whoops, I'll draw a little picture for this, right? So let's say we have a stationary observer and then we have a moving observer, and the moving observer is starting at a point A and they're moving towards a point B. Okay. And let's say that the moving observer is has his clock, and his clock is just measuring time there, right? So we have let's make this a little bit nice. So 12, 3, 6. We just have we're measuring time, right? So the stationary observer is looking at the moving observer, and the moving observer has his stopwatch out so that the stationary observer can see. Okay. So the stationary observer would look at this experiment that's happening, look at this motion, and they would say, well, I think that in the time it takes for your watch to tick from getting from point A to point B, I've observed you moving, so LS, so I measure a distance LS between A and B, and that distance that I measure is going to be equal to V times the time that you're measuring. Okay. Does that make sense? Now, when we flip this picture around, right, when we have the moving observer is just hanging out, and they're observing what's happening with the stationary observer, right? Again, the stationary observer, relative to the moving observer, it's as though the stationary observer is actually moving as well, right? And so what they conclude, well, in my frame of reference, I'm measuring the same distance from between A and B as V times delta TS, right? And that's what I think the measurement is, okay? And so what we're going to do is we're actually going to plug both of these quantities into the formula that we have here, right? Because we notice that we have V times Tm, that is equal to Ls. And we also have V times Ts, that's equal to Lm, all right? And when we make that substitution, we've kind of gotten rid of the times, right? These formulas no longer depend on time. They only depend on length, okay? And when we rearrange this, we again have the length in terms of, or the length in the moving frame in terms of the length in the stationary frame, times the same factor that we had for time dilation, okay? So again, we have some sort of influence of the speed at which an object is, or at which an observer is moving. Length also seems to be affected in a similar way, okay? But one thing we'll notice is that instead of being, so time gets stretched out, right? What we'll notice is that length gets smaller. Length is contracted, okay, instead of dilated, okay? So let's do a quick example here using this formula again. Also, Jana, to go back to like your earlier point, you don't really need to know how to derive all of this stuff, right? You don't need to know all of this stuff in the brackets here. Again, I would say it helps to understand that stuff, but really you just need to know this kind of final formula here, okay? All right, let's do an example to just kind of see how this works in practice. So here we have a similar setup to the last example. We have an observer on Earth, and they're measuring a spacecraft. And specifically, they're looking at the spacecraft and they're saying, oh, well, when I look at that spacecraft is moving at a speed v is equal to 0.700 c. And when I'm looking at that spacecraft outside, I observe it to be 78 meters long, okay? So that's my observation that I'm making on the moving spacecraft, right? So L, the length in the moving reference frame, is equal to 78 meters, okay? Now, what we want to figure out is we want to figure out the, I use a term here that I haven't defined yet, the proper length of the spacecraft, okay? What I mean by proper length, so the LS and the LM in this formula here, LS is called the proper length, and LM is called the relativistic length. That also goes for time, right? We have delta Tm is equal to delta Ts over 1 minus v squared over c squared. These are also called the proper time and relativistic time, okay? Okay, so in this question, we are told that the relativistic length is 78 meters. Now let's figure out the proper length of the spacecraft. So we're trying to figure out what LS is. Okay. So this works kind of the same way as the time dilation questions worked, right? We just plug into this formula and rearrange for the thing that we're looking for. Okay, so we find that LM is equal to LS times the square root 1 minus v squared over c squared. Now because I'm looking for LS, I'm going to rearrange this thing, right? So I find that LS is equal to LM over 1 minus v squared over c squared. Okay. And I'm just going to plug in all the things that I have here, right? So LM is 78 meters over 1 minus, 1 minus v squared, so that's 0.700 c squared over c squared. All right. Now I'm just going to plug this in, see what we get. All right. I get a value of 109.2218466 meters, approximately 3 sig figs, so 1.09 meters. Okay. So essentially what this means is that, Tycho, if you're standing on Earth, right, you're looking in a telescope and you look out at the spaceship. You see it and you measure it to be 78 meters long, okay? Now, Aiden, you're in that spaceship, you turn it around, you come back home, and you land. Now, Tycho, when you look at that spaceship when it's on the ground, when it's not moving anymore, you observe it to be 109 meters in length instead. Okay? So when it's moving, to us back on Earth, it appears to be shortened in the direction that it's moving. Okay? It kind of, you would look at it and imagine it's kind of like squished, right? Like if you take a, I don't know, I'm trying to find an example here, but I don't really have one. Like, okay, so you take this dinosaur, yeah? And this dinosaur is traveling close to the speed of light, right? And so when we observe this from a stationary frame, we would observe it kind of squished in the direction that it's traveling, okay? And so that's how length contraction works, right? You kind of just see it contracted. You see it squished in the direction of travel, okay? So the spacecraft would look something like this, right? However, when we bring that spacecraft back to Earth, it's back to normal, right? It has the same length that it does on Earth, right? Any questions about that? All right, so last thing here. So since time and length are relative quantities, we might expect that other quantities that we've encountered earlier in the course are also relative. So remember that from chapter 5, we had a formula for momentum, right? Momentum was equal to the product of mass and velocity, okay? Now, since the speed at which an object is traveling depends on the distance that it travels and the time that it takes to travel, well, it depends on time, right? So already right there, we would expect momentum to also be some sort of relativistic quantity, right? And indeed, when we change up this momentum formula, so again, I'm bringing this momentum formula down, and then I'm replacing my speed with the distance that it's being traveled over time. Now, suppose that this is the momentum that's being measured from the stationary frame, okay? And so what we want to do is figure out, okay, well, is momentum different in the moving reference frame, okay? And indeed, what we'll see is that the momentum is different in the moving reference frame, okay? And so notice here, what I'm going to do is I have a delta TS in the denominator here. I also have a formula for delta TS. I developed that at the start of today's lesson, right? That's a formula for proper time in terms of the relativistic time. When I plug that formula into my momentum formula, I get this big jumbled up mess here, okay? Now, in this big mess, I notice that, again, I have a delta dx over a delta tm, right? This delta tx over delta tm is equal to v, right? And so what I find there is that I have a formula for the momentum in the moving frame, and the momentum in the moving frame actually depends on the momentum in the stationary frame as well, okay? And so there's again a relationship between the relativistic momentum and the proper momentum of the object, okay? But in this case, we don't call it the proper momentum like we did with proper time and proper length. What we call this is the classical momentum. Okay, meaning it's the momentum in the classical sense, right? It's Newtonian momentum. Okay. All right. One thing we have to be extremely careful about is the fact that we're using mass in this equation, right? It turns out that mass we're also going to see that it is sort of a relativistic quantity, right? We're gonna check in on that tomorrow or on Monday. And so the fact that we're using mass here is a little bit sketchy, but what we have to be a little bit careful about here is that the mass that we're using in this equation is called the rest mass. Okay. So it's the mass of the object when it's stationary. Okay, so we have to be a little bit careful here. All right. So this formula gives us the relativistic momentum, right? So P on the left-hand side of this equation is called the relativistic momentum. Just like we had relativistic time and relativistic length, okay? And so let's do one quick example and then we're done for the day, okay? So here we have an experiment and we're gonna study the properties of subatomic particles. And what we're doing in this experiment is we're accelerating electrons to speeds that are very close to the speed of light. We are told that an electron has, the mass of an electron, and we have to be careful here. This is the rest mass of an electron, is 9.11 times 10 to the negative 31 kilograms. And this electron is moving at a very, very high speed. So a speed that's very, very close to the speed of light. 99% the speed of light. So 0.99 c. And we need to calculate two things. We need to calculate the electron's momentum using the non-relativistic or the classical momentum equation. And then we're going to calculate the electron's relativistic momentum. And then we're just going to compare the two to see what we see. Okay. So the non-relativistic, the classical momentum, I'm going to call that P classical. That's the same kind of momentum that we calculated in chapter 5, right? So just m times v. So m times v So that's the mass of the electron, that's 9.11 times 10 to the negative 31 kilograms, times the speed at which it's moving, so 0.99 c. Let's see what we get when we do that. So 9.11 times 10 to the negative 31 times 0.99, the constant is 28. I get a value of 2.703798199 times 10 to the negative 22, and the units there are kilogram meter per second. Okay, I can round that to 2 sig figs, so 2.7 times 10 to the negative 22 kilogram meter per second. Okay. So I found the classical momentum. That's good. Now let's find the relativistic momentum, right? So P relativistic is going to be equal to this big formula that we have up here for the relativistic momentum, all right? So we have mv over 1 minus v squared over c squared square rooted. Okay. So same idea. Let's plug in all the things here and see what we get. So we have m, which is 9.11 times 10 to the negative 31. V is 0.99 c. So there's our classical momentum. But then we have to multiply by, or divide by this factor here. So 1 minus 0.99 c squared over c squared. Let's see what we get. So over square root of 1 minus 0.99 squared. I get a value of 1.916671726 times 10 to the negative 21 kilogram meter per second, which is equal to, so applying sig figs here, I got 1.92 times 10 to the negative 21 kilogram meter per second. Okay. And so now let's actually just quickly compare these two, right? I look at both of these. I look at my P classical and my P momentum. Now when I compare these two, let's do P, my relativistic momentum, and let's divide it by our classical momentum. And what we should see is about a factor of 10, maybe a little bit less than 10 increase. So 1.92 exponent negative 21 over 2.7 exponent negative 22. Yeah, so about a factor of 7 increase. Okay. So that means the relativistic momentum is about a factor of 7 times as great as the classical momentum, right? So we conclude, therefore, the relativistic momentum is approximately 7 times the classical momentum. Okay. Now, that might not seem like a whole lot. Oh, 7 times, it's not really a big deal. But imagine trying to do one of these like high-energy physics experiments, right? So imagine that, Aiden, you're a researcher at the Large Hadron Collider, and you're firing these things together at speeds very, very near the speed of light. If you're not taking into account the fact that momentum is different when things are moving very fast, well, your experiment is pretty much garbage, right? Because you're missing like a factor of 7 when you're trying to conduct this experiment, right? So accounting for these sort of relativistic effects when things are moving at very high speeds becomes increasingly important when you're trying to apply this in like experimental settings or what have you. Okay. Any questions about anything we've done today? So time dilation, length contraction, relativistic momentum. Any questions about that?